also the electric force. And so the total force on a moving charged particle would then be Q times the electric field vector plus V cross B. And this, of course, we've seen before. An electric field can do work on a charge. Remember, Q delta V can be positive, can be negative, but it can do work. It can change the kinetic energy of the charge. Magnetic fields can never do work on a moving charge. And the reason is that the force is always perpendicular to the velocity v. And so if the force is always perpendicular to the motion, you can change the direction of the motion, but you can't change the kinetic energy. And so that's a fundamental difference between the electric force and the magnetic force. So now I want to calculate with you the force on a current that runs a wire I through it, and we have a magnetic field B. So we're going to be more and more quantitative. This, by the way, is often also called the Lorentz force, just a combination of the two. That one certainly is. So let us start with a wire, and the wire runs a current through. Here's the wire, and the current is I. And let's say at this point here, we have a magnetic field, B. And the magnetic field could be different along the wire, in principle. Here, I have a charge plus dq, and this charge is running through the wire with a drift velocity vd. Let's first think about what happens if the current is zero. If the current is zero at room temperature, these free electrons in these wires have huge speeds, 3 million meters per second, way larger than the drift velocity. But they are in all chaotic directions. Random motion, it's a thermal motion. And so on each individual charge, there will be a force, but they average out to be zero. It's not until I run a current that these charges are going to walk through with a very slow drift velocity, and now, of course, the net force is not zero. So let's have this charge dq that moves in this direction, and so that gives me a current. And let this angle be theta between them. Theta is going to be important because it's a cross product between velocity and b. That means the sign of this theta comes in later. You will say, I hope you will say, well, listen, man, this is ridiculous. Positive charges don't move through wires. It is the electrons that move through wires. They are responsible for the current. And electrons have a negative charge, and they go in this direction. You're right. Perfectly fine. However, a negative charge going in this direction is mathematically exactly the same as a positive charge going in that direction. In both cases do we agree that the current is in this direction. So I have preferred, for mathematical reasons, to take a plus dq charge going in this direction rather than taking a minus dq charge that goes with the drift velocity in that direction. So there is no difference at all in the outcome that you will see. So on this charge, there is a force dF. This is this magnetic force, and that is the charge dq, that equation, times v cross b. Well, v was that drift velocity, and here is the magnetic field at this location. The current through the wire, everywhere in the wire, must be dq dt, because that's the definition of current. How many coulombs per second? The current is always dq dt. So I can also write this as I dt times Vd cross B. But I remember 801, that Vd times dt, that is a speed times a time, is a distance. And I call that distance dl. It's a distance along the wire. I will put the distance in here now because I don't want to clutter up my drawing. So this charge in time dt moves over that distance. That's a vector, 801. So I can write down for this product, I can write down dl. So I can also write down that df of b equals I times dl cross b. What is this telling you? This is the force of a wire over a small segment of the wire which has length dl. I is the current through the wire, and B is the local magnetic field at that location dl. That's what it means. And if you want to know the entire force on the wire, you have to do the integral along the whole wire. And so you have to do an integral along the entire wire, and at every portion dl you have to determine what B is, and you get then a force, which is a vector, and you have to add those vectors vectorially. Could be a pain in the neck, but that's the basic idea. So now I want to calculate what the force was on this wire roughly when we ran 300 amperes through there. And I make a geometry so simple that we can execute that integral. This was the wire, and we had a current running through here which was 300 amperes roughly. And we have a magnetic field which was right in the gap there. That magnetic field, B, and that was 0.2 of a Tesla, 2 kilogauss. And that magnetic field was only operating here, wasn't operating there. And I make the assumption, which is a simplifying assumption, that that magnetic field was constant over a portion of the wire which was, say, only 10 centimeters. And so I assume here that I have a length which is 0.1 meter, and that in this range here, the magnetic field is constant. I just want to get a rough number for the force on that wire. So now I can integrate that equation very easily because I have assumed that the magnetic field is perpendicular to the direction dl, because dl is now in this direction. So the sine of theta is 1, so I don't have to worry about that. And so I simply get that the force on this section F, on this